Welcome to Session 2. In this session, you'll learn how to identify where climate risk concentrates and why some areas face higher impacts than others. We'll use 5 practical mapping tools to do this: urban heat mapping, elevation models, hotspot platforms, overlay methods, and vulnerability assessment. These are the same tools used in professional climate risk practice. By the end of this session, you'll know how to combine these tools to pinpoint priority risk areas. Session 2 moves from theory to spatial precision. By the end of this session, you will understand how terrain, elevation, and urban design shape hazard exposure. You will apply overlay logic to detect compound risk hotspots. You will differentiate hazard intensity from vulnerability concentration, which are not the same. You will rank priority zones using spatial evidence, and you will evaluate infrastructure and population exposure in a defensible way. This is where mapping becomes capital strategy. Urban heat islands make some areas much hotter than others. Cities are often warmer than nearby rural areas, especially at night during heat waves. This happens for 3 simple reasons. First, heat storage. Concrete and asphalt absorb heat during the day and release it slowly after sunset. Second, dark surfaces. Black roofs and asphalt absorb most of the sun's energy and hold it. Third, human activity. Cars, buildings, and air conditioners release heat directly into the air. These factors build on each other. Dark surfaces absorb heat, buildings store it, and AC units push even more heat outside at night. The result is sustained high temperatures in certain neighborhoods, even long after the sun has set. During a heat wave, these areas face the greatest health risks and often need the most support. The good news is that urban heat islands can be reduced with targeted actions. Trees make the biggest difference. Shade from trees can cool surfaces, and parks create cooler zones that are several degrees lower than the surrounding built areas. This is why expanding tree canopy in hotspot neighborhoods is so effective. Cool surfaces also help immediately. White or reflective roofs stay much cooler than dark roofs. Light-colored pavement also absorbs far less heat than black asphalt. These upgrades are simple and provide rapid, measurable cooling. Water features add local cooling through evaporation. Small misting areas or fountains can lower temperatures. Smart design also reduces heat at the source. Walkable streets mean fewer car trips and less heat from traffic. Energy-efficient buildings reduce the amount of heat released by cooling systems. When these strategies are layered, trees, cool roofs, light pavement, water features, and efficient design, the combined cooling effect is strong. This protects vulnerable residents and reduces stress on infrastructure during extreme heat. Digital elevation models, or DEMs, are a core tool in climate mapping. A DEM shows the height of every point on the landscape. Most are created from LiDAR, radar, or satellite data. High-resolution LiDAR can map elevation with remarkable detail. Elevation matters for several reasons. Low-lying areas, especially those below 3 meters, face higher flood and storm surge risk. DEMs help identify where flood protection or elevation improvements are needed. Valley bottoms often trap heat. These areas can be several degrees hotter during heat waves. DEMs help you spot these zones so you can plan cooling centers and target resources. Steep slopes face landslide risk. DEMs help guide development decisions and early warning system placement. During storms, DEMs show where water flows, where it collects, and which roads or buildings flood first. Along the coast, they reveal which facilities are most vulnerable to inundation. In short, terrain shapes climate exposure. DEMs make that exposure clear, measurable, and actionable. Different colors show differences in elevation. Stepper terrain is at greater risk of landslides to your assets. Hotspot Explorer platforms put climate risk mapping directly in your hands. You don't need a GIS background or specialized software. Everything runs in your web browser. These tools combine three types of data. They show hazards like heat, flooding, drought, wildfire, and storms. They show exposure, such as population density and key infrastructure. And they show vulnerability, including income levels, age, health conditions, and other factors that affect how people cope. Using them is simple. You select a location, choose the hazards you want to examine, and then apply vulnerability filters. The results appear instantly with color coding. Green shows low risk. Red shows extreme hotspots that need urgent attention. You can work at any scale, start with a region, then zoom down to specific neighborhoods or individual facilities. These platforms help answer practical questions. Which areas face multiple hazards at once? Where are vulnerable populations most exposed? And where should limited adaptation resources go first? This map shows regions at greatest risk of water stress with 1.5 degrees warming. In the next slides, we'll look at real examples of how these tools are used in practice. This example shows how two cities in the same region can have very different levels of heat vulnerability. City A has good tree canopy, newer infrastructure, and higher incomes. It also has a smaller elderly population. Even during high temperatures, its overall heat vulnerability stays relatively low. City B is very different. It has few trees, older infrastructure, lower incomes, and a large elderly population. These factors make City B far more vulnerable to the same level of heat exposure. The platform makes these differences easy to see. It highlights where heat exposure is high, where populations are sensitive, and where adaptive capacity is low. This information is extremely useful for planning. Cities with the highest combined risk move to the top of the priority list, often for actions like expanding tree canopy, improving cooling access, or upgrading aging systems. Cities with lower scores may only need targeted improvements. The result is clear, evidence-based prioritization. Limited resources go where they reduce risk most effectively, and decision-makers have solid justification for budget requests. This map can be zoomed in to view cities relative to the heat stress. More people and assets are exposed in the cities. This example shows how hotspot tools help identify vulnerable critical infrastructure. Imagine a coastal area where several major facilities sit at low elevation. A hospital is located inside a high-risk flood zone. During a severe storm, it could lose road access or electrical service, exactly when medical care is most needed. A nearby power substation sits in another flood-prone area. If it goes offline, tens of thousands of residents could face long outages. A water treatment plant in a low-lying zone could be contaminated or forced to shut down during coastal flooding. The main concern is the cascade effect. If the substation floods, the hospital loses power. If the water plant shuts down, health and emergency services are disrupted. One failure can trigger widespread system breakdowns. Hotspot platforms make these dependencies visible. They produce a clear, ranked list of which facilities face the highest flood exposure and have the greatest community impact. Those sites move into Priority 1 and require immediate protection, upgrades, or relocation in capital plans. The result is a focused roadmap. Which assets need attention first, and what level of protection is appropriate. This helps build a strong and defensible infrastructure resilience strategy. The greatest flood risk is adjacent to riverbanks. Infrastructure exposure for destruction is high along rivers. This flood risk map shows how exposure intensifies along the river corridor, with very high-risk zones, in red, concentrated near riverbanks where critical infrastructure is most vulnerable. Hotspot mapping becomes far more useful when you follow a simple, repeatable workflow. The goal is to move quickly from raw data layers to a clear, ranked map that shows where multiple hazards and vulnerabilities overlap. This workflow also helps link each hotspot directly to an intervention so users can move from analysis to action without getting lost in technical steps. The steps are: 1. Define objective. What decision are you supporting? For example, heat mitigation investments, flood mitigation. 2. Gather core layers, compile hazards, elevation, population, infrastructure, vulnerability indicators. 3. Map single hazards, visualize where each individual hazard, heat, flood, wildfire, occurs most intensely. 4. Overlay multiple hazards, identify locations where hazards stack and create compound risks. 5. Add exposure, highlight assets, infrastructure, and population areas located within these hazard zones. 6. Add vulnerability filters. Apply socioeconomic and demographic layers to pinpoint communities with limited coping capacity. 7. Rank hotspots. Score each area based on hazard severity, exposure, and vulnerability. 8. Prioritize actions. Assign realistic interventions to each hotspot based on the drivers of risk. To illustrate this, consider a practical example from an Australian metropolitan area. The city followed this exact workflow to guide climate resilience investments. Define objective. The city aimed to target funding for cooling, drainage upgrades, and community heat health support. Gather layers. They collected heat island data, flood-prone areas, elevation, road networks, building footprints, and census indicators for income, age, and housing quality. Map single hazards. Heat maps revealed western suburbs consistently experiencing higher surface temperatures. Flood maps highlighted known flash flood corridors. Overlay hazards. When heat and flood layers were stacked, several districts faced both high heat and recurrent flooding. Add exposure. Schools, aged care facilities, and dense housing blocks were mapped to show which populations were directly in harm's way. Add vulnerability. Low-income households, older adults, and poor quality housing concentrated in these same districts elevated them further in the ranking. Rank hotspots. Suburbs that repeatedly scored high across hazard, exposure, and vulnerability metrics became Priority 1 zones. Prioritize actions. Streets with extreme heat, plus high elderly populations, leads to tree canopy expansion. Flood-prone roads near schools, leads to drainage upgrades at critical choke points. Neighborhoods with older adults, plus recurring heat stress, leads to targeted heat health outreach programs. Hotspot identification follows a simple, structured method. Each data layer, hazards, elevation, exposure, and vulnerability, is scored for severity. When high scores stack in the same place, a hotspot emerges. There are 4 clear steps. Step 1. Map a single hazard. Start with one hazard, such as extreme heat, to see where it concentrates. Step 2. Add a second hazard. Overlay another layer, like flooding. Where the colors overlap, you start to see compound risk. Step 3. Add exposure. Overlay population, infrastructure, and key facilities. This shows exactly what sits in harm's way. Step 4. Add vulnerability. Layer income, age, health, and other sensitivity indicators from census or community data. Areas that score high across all layers, high hazard, high exposure, and high vulnerability, become extreme hotspots. The result is a clear, integrated risk map. Deep red zones point to Priority 1 areas for adaptation planning, where multiple hazards align with the most sensitive populations and the lowest adaptive capacity. This method takes complex climate data and turns it into focused, actionable priorities. It helps move planning from analysis into real implementation. Two or more sectors are exposed. These are the hotspot zones. This map illustrates how stacking multiple hazard, exposure, and vulnerability layers reveals compound risk hotspots, areas where climate threats align with sensitive populations and critical assets. Climate hazards do not affect everyone the same way. Some groups face much higher risks, so it's important to identify and protect them. 5 main factors drive vulnerability. Age is the first. Older adults and young children face higher physical stress during heat, smoke, or storms. Adults over 65 make up most heat-related deaths nationwide. Income is another factor. Lower-income households often have fewer resources to prepare, evacuate, or recover. Many lack air conditioning, reliable transportation, or adequate insurance. Health conditions also matter. People with respiratory or heart conditions are more sensitive to heat, smoke, and poor air quality. Housing quality plays a major role. Older homes, rental units in poor condition, and mobile homes offer limited protection from extreme heat, storms, or smoke. Language and cultural barriers can also increase risk. Limited English proficiency may delay access to warnings, assistance programs, or evacuation instructions. When several of these factors overlap, vulnerability becomes extreme. For example, an older adult with health issues, living in poor quality housing, without reliable cooling or transportation, faces very high risk during a heat wave or wildfire smoke event. Mapping where these populations cluster helps identify priority areas for cooling centers, targeted alerts, and support during emergencies. It ensures adaptation efforts reach the people who need them most. Critical infrastructure keeps communities functioning, so understanding where it is vulnerable is essential. When one system fails, it can trigger disruptions across others, making early identification of weak points a top priority. The power grid is a clear example. If a substation floods or overheats, entire districts can lose electricity. Mapping these risks helps planners decide where to harden equipment or add backup generation. Water systems face similar threats. A treatment plant in a flood zone can be forced offline, cutting supply when demand is highest. Hazard overlays highlight where protection or relocation may be needed. Transportation networks and communications networks are other critical infrastructure. Roads must stay open for evacuation, emergency response, and supply chains. Cell towers, fiber lines, and data centers must remain operational during storms. Even short outages can limit warnings, coordination, and emergency services. Healthcare facilities are among the most important assets to protect. Hospitals need resilient power, protected structures, and dependable access routes to operate during extreme weather. Overlaying infrastructure networks with hazard maps quickly reveals the weakest links: a substation in a floodplain, a hospital with limited access, or a treatment plant without backup power. These sites become top priorities in capital plans. This graphic highlights the core systems: energy, water, transportation, communications, health, finance, food, and government that must remain resilient as climate risks increase. Session 2 delivers 5 strategic insights. Risk is spatially uneven. Impact concentrates geographically. Overlay analysis reveals leverage points where intervention produces the greatest return. Compound exposure defines priority 1 districts. Infrastructure risk is network-based. One failure can cascade. And targeted investment outperforms uniform spending. Precision drives performance.